Okay, so we took a little detour the last three modules and really focused on the solar system. Remember, we studied the sun in Module 6, and in Module 7 we studied the inner planets, and then in Module 8 we studied the outer planets and kind of the solar system debris. Now I want you to go back in your head, back to Module 5, and remember we really focused on light in Module 5, and you're going to need to know some of that information. Well, remember, why do we study light? Why do we talk about light? Because light is what astronomers have to work with. And where does the light come from? What is the light we're interested in? It's those stars out there. Okay. And what you're going to find out in this module is how much information astronomers can extract from those little pinpoints of light. From those little pinpoints of light, we've already discovered that we can find out the composition of stars. We learned about the different absorption spectra and how that tells you the composition of stars. We've also learned a little bit about the relative motion of stars. We've learned, we can tell if they're moving away from us, moving toward us. That's all due to Doppler shifting. Now we're going to talk about some other things we can learn about stars, such as their size, how far away they are, how hot they are, et cetera, et cetera. So that's what I really want you to focus on in this module. And another thing we're going to learn in this module is that there are different types of stars. They make up this entire family. And so we're going to learn about that as well as the typical life sequence. A family is made of individuals, and all those individuals go through lifetimes, right? And stars do the same thing. There's a family of stars out there, and they're all at different life stages. They're all different types of stars, and they're all at different stages in their lives. So we're going to learn about that primarily in this module. The first topic introduced here in Chapter 13 is a topic called parallax. And parallax is really a way of determining the distance to stars. And one of the first things you have to remember, and I think we introduced this a while back, but I want to reintroduce it because you sort of need to understand this to understand parallax, is the concept of what are called arc seconds. Now, so imagine I've got two stars there on my wall. Can you see those? I've got two stars, and I want to talk about how far apart are they in the sky. Well, it's tough to, if those were truly two stars in the sky, I couldn't say, oh, they are a certain number of miles away, because I really don't know that. I don't know how far physically apart they are. But I can use angles to tell you how far away they appear to be in the sky. If I consider my sky as being, remember, the celestial sphere, and I start at one horizon and I look straight up. Remember that we talked about a 90-degree angle is what you call the zenith. And if I continued to my other horizon, that'd be 180 degrees, right? So I can actually divide the celestial sphere, my sky, into 180 degrees from this horizon to that horizon. So therefore, I could talk about a certain number. Oops, one of my stars just fell down. I could talk about how far in degrees it is from one star to the next. And here's a little rule of thumb, or rule of finger, perhaps. The pinky finger at an outstretched arm's length is about 1 degree apart. So I can stack my pinky. If I could do this 90 times, I would wind up at my zenith. And so that's one way of determining how far apart two stars are in the sky, is by measuring in degrees. And you can do that by using your pinky. If you get tired of stacking pinkies, you can use 3 fingers, your little Boy Scout salute or Girl Scout, whatever. Put those 3 together. That's about 5 degrees at an outstretched arm's length. Your entire fist is about 10 degrees. If you stretch out your thumb and your pinky finger this way, that's about 20 degrees. So in doing this, I can do this about 4.5 times. And that would get 4.5 times 20, 90 degrees. That would take me to my zenith. Now, once you understand what a degree is, that's still a fairly large amount of space. That's a fairly large distance in my celestial sky. So as this diagram indicates, you can actually break 1 single degree down. So we notice that this single degree gets expanded, and 1 single degree can be broken into what are called 60 arc minutes. And then each arc minute can be further broken down into 60 arc seconds. So it turns out that 1 degree in your sky is actually equivalent to 3,600 arc seconds. Okay, so we've dealt with parallax once before. Remember back in chapter 4, module 4, we talked about how the ancient Greeks made the argument that the Earth had to be stationary because the stars all, the patterns all looked the same. The stars didn't really change position with respect to each other, which made them think that the Earth was stationary. And the argument was, what if you stick your thumb up at an outstretched arm's length and point it toward a wall, and then close your right eye and look and see where your thumb is with respect to the wall, and then close the other eye, and you'll notice that your thumb appears to shift. That's what's called parallax shift. Their argument was that's not seen when you look at the stars. And what they failed to appreciate is that stars are really far away, and that's why you're not able to see much of a shift. But it turns out that some stars are closer than others, and it turns out that if you have a nearby star, relatively nearby star, such as this guy, and you're looking at it with respect to these background stars, then it will shift if you view it at one point during the year and then wait 6 months later and look at that same star with respect to those background stars. It does appear to change its position. There is a little bit of a parallax shift there. And if you can measure the amount of parallax shift in arc seconds, then it turns out there's a very basic equation that will give you the distance to that star. And it's just you take 1 divided by the parallax shift in arc seconds, and you get the distance in a new unit called parsecs, and sometimes that's abbreviated PC. And it turns out that 1 parsec, and again, this is a new measuring stick now, because in space, as we've talked about, distances get really big. So our nearest star is the Sun, 8.3 light minutes away. The next nearest star is Proxima Centauri, 4.3 light years away. But the distances can even get large when you start talking about light years, and therefore we need to have a new measuring stick, and the new measuring stick is the parsec, and it turns out that 1 parsec is equivalent to 3.26 light years. That's how far away a star would be that shows 1 arc second of parallax shift. That star would have to be 1 parsec away, otherwise known as 3.26 light years. Okay, so to give you a feel as to how this calculation works, here's a little simulation that does the work for you, does the math for you. So let's imagine we've got a star, and that star, when we view it during the course of a year, exhibits 1 arc second of shift against the background stars. Now remember what an arc second is. Remember, your outstretched pinky finger is 1 degree wide. And 1 degree is the same thing as 3,600 arc seconds. So you would have to slice your pinky into 3,600 equal slivers. One of those slivers would be equivalent to an arc second. So that's how much shift a star would have to produce against the background stars to have 1 arc second of parallax shift. Now let's think about, and obviously the math here is pretty easy then. If that star does show 1 arc second of parallax shift, you do 1 divided by 1, you get the distance of that star being 1 parsec away. And of course 1 parsec is equivalent to 3.26 light years. So we could say that star is 3.26 light years away. Now let's use a real example. Let's think about our next nearest star, which is Proxima Centauri. It turns out that Proxima Centauri, if we look at it during the course of a year, it only exhibits a parallax shift of 0.76 arc seconds. And that's our next nearest star. And yet it shows just a small little shift, unnoticeable to the human eye, but to our telescopes, we can actually measure that amount of shift. 0.76 arc seconds of shift winds up resulting in a distance for Proxima Centauri of 1.32 parsecs. And that's equivalent to 4.29 light years. So indeed, our Alpha Centauri is about 4.3 light years away. That means that the light that we receive from Alpha Centauri or Proxima Centauri takes about 4.3 years to get here. Way back in Module 1, we talked about apparent magnitude. How bright does a star appear to be when viewed from Earth? But that doesn't tell us very much about how truly bright that star is. In order to find out a star's true brightness, we need to know something about its absolute magnitude. Because it turns out that you can have 2 stars. In fact, down here at the bottom of the screen, you see 2 stars that may appear equally bright from Earth, but it turns out that star A is intrinsically brighter than star B. This is the much brighter star, but notice that it's also more distant. And it turns out that distance has an impact. It's very much like if you had a candle held right up to your eye, it would look really, really bright. You take that candle all the way down the street, and you might not even see that candle anymore. And so that the candle has not changed its brightness. It appears to be less bright, and that's only because of a function of distance. So it turns out that we need to somehow figure out a way to level the playing field and be able to compare apples to apples when we're comparing stars. Okay, I wanted to show you a little simulation to make the point that just because a star appears to be bright does not necessarily mean that it is truly a bright star. So here we have two light bulbs, and they're equal brightness in the sense they're both 25-watt light bulbs. And notice I've got a little detector here, and when I'm a distance of 1 away, I get the same amount of light received by this particular little detector. Now, notice what happens when I move farther away. Well, gosh, now I go twice as far, and notice what's happened. My receiver is now only receiving 0.5 units of light compared to this other guy, which is receiving 2 units of light. Well, notice the difference there. 2 compared to 0.5. Isn't 2 4 times greater? So notice by doubling my distance away from my light, I've actually decreased my amount of light received by a factor of 4. And what if I go extremely? Let me go all the way out to 5. Right? If I go way out here to distance 5, now I'm receiving 8/100ths of a unit of light compared to the 2 units of light that I'm receiving at my other detector. And then it turns out that because I'm 5 units away now, I'm actually receiving 1/25th the amount of light that the other detector is receiving. So now let me go and let's change the actual brightness of the light. Let me crank this guy up to be 4 times as bright. I went from 25 watts to 100 watts. I made this 4 times as bright, and notice that sure enough, at the same distance, this receiver is receiving essentially 4 times as much light. Now, how can I make them receive the same amount of light? Notice what happens when I back this up to, if I double the distance, notice that now my reading is the same. So despite the fact this is a light bulb that is 4 times brighter, my receiver is also twice as far away, and therefore the amount of flux, it turns out, the amount of light received at each of these locations is the same. So determining the relative, the true brightness of a star is a pretty tricky business. And you can't just say that a star is a really bright star just by virtue of the fact that it appears bright to us from here on Earth. Because if that were the case, then certainly the sun, we would say, is the brightest of all stars, because certainly it appears to be the brightest. And as we're going to find out, it clearly is not the brightest star in the sky. Okay, so in order to compare apples to apples, we have to level the playing field. We use something called absolute magnitude, but it actually works similar to apparent magnitude. Remember apparent magnitude? I think I may have mentioned, my recommendation is always to choose use a little number line and think about, gosh, the apparent magnitude. This is lowercase m. The apparent magnitude of the sun is like -26. That's where the sun is, and here's 0, obviously. And like Polaris is, I forget, it's like a positive, or let's say Venus can get to be like -4 sometimes. So the farther left you are on this number line, the brighter the object. So in this case, the sun, -26, Venus, -4. The sun is brighter than Venus, so therefore on the apparent magnitude scale, it's to the left of Venus. The same thing goes for the absolute magnitude scale. Usually that's given as a capital M, but you get the same thing. You get the, so in the case of absolute magnitude, it turns out that our sun winds up being over here, like at I think it's about a 4.83 is its magnitude on the absolute magnitude scale. So how is that? Why is that? It's because absolute magnitude is defined as the magnitude, how bright a star would appear to be if we were able to move it to a distance of 10 parsecs. Remember that a parsec is 3.26 light years, so therefore 10 parsecs is going to be equivalent to 32.6 light years. So if we could take our sun, and instead of having it be 8.3 light minutes away, if we could move it off into space and move it 32.6 light years away and looked at it again from Earth, it would only appear to have a brightness of 4.83. It would still be visible to the naked eye, but it would be pretty tough to see, especially in kind of city lights and urban areas. That'd be a tough star to pick out. So that's a way of leveling the playing field. You know, our sun appears to be so darn bright, not because it's a truly bright star, but only because it's so darn close. What if we could move it far away and move all the other stars, whether they're really far stars or really close? What if we could all move them to a distance of 10 parsecs away? How would they appear from that location? That's a way of truly comparing the intrinsic brightness of stars, and that system is called absolute magnitude. Okay, so if you remember back to Module 1, we discussed some of the stars in the constellation Orion. Now, first of all, here's Orion. For those who've ever seen it in the nighttime sky, it actually kind of looks like a bow tie with these 3 belt stars and then 4 stars that mark essentially the shoulders of Orion and the ankles of Orion. And it turns out that the 2 that are really going to leap out at you are going to be the left ankle and the right shoulder. The right shoulder is kind of a reddish star. The left ankle is a very bright, almost bluish star. So what do we know about them? Well, first of all, the names are Betelgeuse and Rigel. And numerically, we can put some numbers to it. Notice that the apparent magnitude of Betelgeuse is positive 0.41 and Rigel is positive 0.14. And so we could actually put these on a number line for you to determine, okay, which one is the brighter star apparently. So again, we put our 0 mark, and we notice that, well, shucks, 0.14 is to the left of 0.41. So that means that Rigel appears to be a little bit brighter. It's not a significant difference, but it is to the left of Betelgeuse on the number line, and therefore it appears a little bit brighter. Remember, to the left on a number line means brighter. That's for the apparent magnitude. That's how it appears. That's how these stars appear when viewed from the Earth. Now we also notice we have some information about their absolute magnitude, or their capital M. The absolute magnitude, I'm going to put my 0 mark here, of Betelgeuse is negative 5.5. And the absolute magnitude of Rigel is negative 6.8. So indeed, Rigel, not only does it appear to be the brighter star, but it is actually the brighter star. The reason being its absolute magnitude is also to the left of Betelgeuse. So in the apparent magnitudes, we don't really know how far away these stars are. All we know is that the one appears brighter in our sky. The absolute magnitude, now we level the playing field. We put them both at the same distance from the Earth. And we say, okay, how would they appear to be if they were both the same distance from the Earth? And it turns out that Rigel, again, is the brighter star, which means that it is truly intrinsically brighter. And there is some little math here. If you actually wanted to know how much more bright Rigel is, well, you could use this 2.512 and you take it to the exponential power that is equal to the difference in the magnitudes, the absolute magnitude of Rigel minus the absolute magnitude of Betelgeuse, and it winds up being 3.3 times brighter. That's not so important. The important thing is that you recognize that Rigel is indeed the brighter star. Why? Because its absolute magnitude is to the left of Betelgeuse's absolute magnitude when viewed on a number line. Okay, I'm going to use a simulator and an equation to answer the question from the last slide, which was, we have a star that's got an absolute magnitude of negative 1.5 and an apparent magnitude of positive 3.5. The question is, how far away is that star? So the way you use this thing is you, first of all, choose your apparent magnitude. Remember, that's the little m. So it told us that this star has a positive 3.5 apparent magnitude. I'm going to go ahead and lock that in. And then we were told that it's got a absolute magnitude of negative 1.5. So what that meant is that this is a truly bright star that appears relatively dim. And the question is, how is that possible? And notice how my star moved as I started to use those sliders. That star, we knew it had to be more than 10 parsecs away. That's what that PC stands for. And it turns out that in order to make the math work out correctly, this star must be 100 parsecs away, 326 light years, in order to make this very bright star appear to be relatively dim to the naked eye. Okay, so we already learned back in Module 5 or Chapter 6 that Stefan-Boltzmann relationship, the fact that a hot star produces a huge amount of energy, more than a cooler star. We learned about the light curve, or the energy curve, and we learned about how the peak in that curve shifts, that Wien's displacement law. We're going to make this a little more mathematical. It's not going to get too mathy, but it turns out that not just a star's brightness, so the amount of energy that it puts off, is not just related to the temperature. It turns out there's actually two factors involved. There is certainly the temperature, but also the size of the star. So notice that the luminosity, or the amount of energy that a star produces each second, depends certainly upon the temperature, but it also depends upon the surface area of the star. And that's given by this equation 4 pi r squared. Where r is really, that's the radius of the star. So the bigger the star, the bigger the r. And therefore, the bigger the 4 pi r squared, because these are just numbers here. These are just constants. So certainly the luminosity, the brightness of a star, depends upon these two factors, the temperature and the area, the surface area. Because the larger star is going to have more area from which to produce energy. So therefore, it will be a more energetic star the larger that it is. But as you can tell, numerically, if you start throwing some numbers in here, think about which quantity, if doubled, would have a bigger impact on the luminosity. Notice that if you double the radius, that doubling gets squared. But think about, what if you double the temperature and kept the radius the same? What's 2 to the 4th power? Well, let's see, 2 to the 1st is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16. So by doubling the temperature of a star, you actually 16-tuple its luminosity, everything else remaining the same. So the temperature is the bigger factor. Both these things are factors, but temperature is more important when it comes to the luminosity, because temperature is taken to the 4th power in the equation. Okay, so as we discussed way back again in Chapter 6 and Module 5, stars have what are called absorption spectra, from which you learn a lot about their composition. All these stars at their core are producing continuous spectra, but then some of the types of light, some of the photons, are being absorbed as that light tries to get out of the star and heads in our direction. It gets absorbed by the star's atmosphere. That tells you something about the content or the composition of the star's atmosphere. And so you wind up with these little dark lines. And it turns out that astronomers then can look at different spectra from different stars and determine essentially the surface temperature of the stars. And they use the spectral classification. O stars, B stars, A stars, F stars, G stars, K stars, and M stars. And your book suggests a couple of mnemonics for it. For me, I like to think of only bad astronomers forget generally known, with a K, mnemonics, with an M. That's one way of knowing your stars. So O stars are hot stars, M stars are cool stars, and then they're kind of graded in between. And each of these actually have, each of these temperature groupings has another breakdown of 1 to 9, I believe. So you can have a G1 star, a G2 star, a G3 star, a G4 star. Those are just more finer gradations in the temperatures. But one thing you'll notice is that a lot of these stars show the same lines. So like these lines here, we've got the Bomber series here of here's the H alpha line. And notice that it's more apparent in, say, an A5 star than it is in a G5 star. And this H beta line, also similar thing going on. Much more apparent in, say, an A star than it is in an O star. And so I suggest you read in chapter 13, page 266, the reason for this, because this actually leads to helping astronomers figure out whether these stars are main sequence stars, whether they're giants, whether they're supergiants, et cetera, et cetera. So not only can you figure out the spectral class, meaning the temperature of the star, you can also figure out essentially the size of the star, what's called the luminosity class, by looking at the size of these different absorption lines. So again, I encourage you to read through that section on page 266 about how to determine the luminosity classes for these different stars. Okay, so rather than seeing a colored spectrum of the absorption spectrum like we saw just a couple of slides ago, this is the same thing. These are stellar spectra, but this is showing the absorption lines as essentially a light curve. Notice we have the intensity, the light intensity at different wavelengths. So it's light intensity versus wavelength. And you can tell, first of all, that the hot stars, the O stars, notice the light curves are much, much higher. They're way, way up here compared to the light curve of an M star, a much cooler star, which is way, way down here, which again, we sort of knew. We also see another trend, that as the star gets hotter, not only does its curve get higher, but its peak moves farther to the left. Notice that for a G star, we seem to have a peak right about there. An M star has its peak a little bit farther to the right. I'm sorry, K star. An F star has its peak a little bit farther to the left, et cetera, et cetera. So we see that Wien's displacement law in effect. We also see these dips, and again, the dips indicate absorption lines. The deeper the dip, the stronger the absorption line. So we can see that not all absorption lines show up the same in different temperature stars. So this H alpha line shows up quite dramatically in an F star, but really does not show up too much in a B star. And again, the reason for that is explained on page 272. I'm actually not going to go into a long, drawn-out explanation of the HR diagram, largely because you're going to be getting a lot of experience with it in the lab activity for this chapter, or for this module, which is indeed all about the HR diagram. Okay, if you didn't already read the discussion on page 272 of your textbook, I encourage you to go and check this out as far as how astronomers, and this is to me part of the beauty of astronomy, is that, first of all, it's amazing that astronomers figured out that they could take light from stars and create a spectrum out of that light. And then it's also amazing to me that they were able to figure out that, well, gosh, the missing lines in those spectra, those absorption spectra, tell us something about the chemical composition of those stars. And even more fascinating to me is the fact that they can actually measure the breadth or the broadness of those absorption lines, and from that they're able to figure out something about the size of those stars. Again, these are little pinpricks of light, and through reason and through observation and through physics, they're able to tell so much about these little pinpricks of light, despite the fact that we have no hope of ever actually going to them and visiting them and sampling them on our own. We still know a tremendous amount about these stars remotely. Okay, so again, when you have a large collection of stars and you start sampling, getting information about their temperatures as well as their luminosities, you can start plotting them. And it turns out that the majority of stars are going to wind up falling on this line that's labeled by the Roman numeral 5, V. Those are main sequence stars, but not all stars fall along that line. There are stars that fall both above and below the line, and the ones that are above are giants, supergiants, subgiants. There's different luminosity classes. And again, page 272 of your textbook explains a little bit more about those different luminosity classes. Okay, so the question asks us, what is the radius and luminosity of a star that is classified as a G2-3? Okay, so we've got this little simulation here that shows an HR diagram with the different luminosity classes. Okay, white dwarfs, or dwarfs and giants, and supergiants, main sequence stars. And so we want a G2. Well, we can choose our spectral type. That spectral type has to do with the temperature of the star. And so I'm already in a G2. And let me go ahead and give it the star that I've got right now indicated as a main sequence. That's a Roman numeral 5. I don't want that. I want a G2-3. And notice that the star now is a giant star. Okay, so a G2-3 means that it is and they want to know is the radius and the luminosity, right? So we know the radius is certainly larger. Notice that we went from being a main sequence star to a giant star. Okay, so it's going to have a larger radius than that of the sun. Remember, the sun is a G2 star. So in comparison, this star that we've just created is a star that is larger than our sun. And if we had those diagonal lines on here, we could figure out how much larger it is. But your book, there's a diagram that shows the different what are called isoradius lines, and so we could ballpark it. I believe it's around 10 solar radii. So this is a star that is 10 times larger. And notice, by being 10 times larger and being the same temperature, look on our y-axis now. If we go straight across, notice that the luminosity, obviously this star should be brighter than our sun. It should be producing more energy. Not because it's hotter, not because it's any different color, but because it's got more surface area from which to be emitting energy. So it is actually producing more energy per second. It's more luminous. In fact, it's 10 to the second power, which is 100 times. So the answer to the last question, which was, what's the radius and luminosity of a star that is classified as a G23? Well, it's going to be 10 times the solar radius, and its luminosity is going to be 100 times greater. Okay, I'm not going to spend a whole lot of time with binary stars, at least not in this lecture mix. And the reason being, binary stars are actually the topic for the lab activity in Module 10. So you're going to learn a lot more about binary stars in the next module. But one thing I will tell you is that our sun is relatively unusual in the sense that it's a cosmic loner. It does not have another star with which it is closely gravitationally bound. At least 50% of all stars in our Milky Way are indeed at least binaries, if not multiple star systems. So our star is relatively unusual in that sense. As you'll learn in the text, binary stars can be different varieties. You have what are called visual binaries and spectroscopic binaries. Again, a binary star is a star that is closely bound to another star. Now, if they happen to, and of course they're going to be orbiting around a common center of mass. If they happen to be orbiting in a plane that is also the same plane as our line of sight, then we'll see one star pass in front of the other periodically. And that's what's called a visual binary, because there's going to be changes in the combined brightness of the light from those two stars. When the one moves in front of the other, it's going to block out the back one, and vice versa. When the back one then winds up moving into the front, it blocks out the light from the back one, et cetera, et cetera. Those are visual binaries, relatively uncommon. So just the plane of orbit just happens to line up with our line of sight. That's a relatively infrequent occurrence. More common is going to be what are called spectroscopic binaries, and that's where the stars are indeed orbiting each other, but the plane on which they are orbiting each other is not the same as, it does not kind of line up with our line of sight. It's somewhat inclined with respect to our line of sight. But nevertheless, they are going to be tugging on each other, and that's going to produce a certain amount of red shift or blue shift. It's going to be a certain Doppler shift on the spectra of these stars. And that will help us to at least put an upper limit on the possible masses. It won't give us an exact value because they aren't on plane. But we can at least get in the ballpark as far as how much mass these stars potentially could have because of the gravitational impact, the Doppler impact they have on each other. One of the last topics covered in chapter 13 is what's called the mass-luminosity relationship. And it's pretty simple to understand. It's just the more massive a star, the more luminous it is. And that's about it. There's actually a mathematical relationship. This holds only for main sequence stars. That's very important to understand. This only works for main sequence stars. But again, if we plot the luminosity of a star with respect to its to the luminosity of the sun, and also plot its mass with respect to its mass, and its mass with respect to the mass of the sun, we get a nice mathematical relationship that shows up. Again, the luminosity is proportional to the mass of the star to the 3.5 power. That's relatively unimportant. What's important for you to understand is that the more massive the star is, the more luminous it's going to be. And that, again, only holds for main sequence stars. Okay, so we just said that the more massive a star is, the more luminous it's going to be. But the more luminous a star is, that means the more energy it's producing. That means, well, it produces that energy somehow, right? And we're going to learn more about how it produces the energy in the next chapter. But it turns out that this does have an impact on the lifetime of a star. So for example, our star, kind of a middle of the road main sequence star, has a expected lifetime of about 10 billion years. And it's been around for about 5 billion years. So it's a middle-aged star. A more massive star, a more luminous star on the main sequence, in this case, a star that is 10 times as massive as our sun, notice how that impacts its expected lifetime. Instead of living 10 billion years, this star is only going to live 30 million years. So despite the fact that it's a much larger star, and you would think it's got a lot more material to work with, it winds up living a much, much shorter life. And we're going to explore that topic later on in chapter 14. Do you know what a census is? Back in 2010, I was employed by the Census Bureau, and I went around and I interviewed people. A census is done amongst populations to learn about the population, to learn about the people who live in the country as far as their ages and their ethnicities and whether they're employed and all that kind of stuff. You get a feel for the individuals who make up an overall population. Same thing with stars. Wouldn't it be nice if we could survey all the stars within a certain volume? We have a problem though. We don't see all the stars within a certain volume, 62 parsecs away. That's a big distance. It doesn't, of course, get all the stars, but even the stars within that volume, we're not able to check up on, because a lot of them are just too faint for us to observe. We tend to be, anytime we do a survey, we get a bias problem, because the ones that we see are the brighter ones. We don't necessarily see the most common ones, we only see the brightest ones. So it turns out that if we just found the brightest stars in the sky and mapped them on an HR diagram, we'd wind up with a graph kind of like the one on the left. If we chose just the nearest stars and we graphed those, you'd wind up with a graph that looks like the one on the right, which shows spectral type versus the luminosity of the nearest stars. And if we combine both of those and wind up doing what's called a histogram, where we not only include, essentially this is an HR diagram that not only includes the luminosity or the absolute magnitude on the y-axis, and it also includes the temperature or the spectral class on the x-axis, but it also has a z-axis here, which is the number of stars per million cubic parsecs. Essentially, it's a volume measurement, and the number of stars per a certain amount of volume. And it shows that according to the height of these bars. So what we see overwhelmingly is that the most common type of star is a red dwarf. And in fact, the number of giants and supergiants when plotted, and even upper main sequence stars, wind up being so small that they don't even register as a column. So this is a very important diagram for you to understand. This is off of page 283 in your textbook. So I'd spend some time understanding this one, not only to understand the HR diagram, but also the fact that this is a histogram. This shows the population of the respective type of stars on the HR diagram. If you recall, a couple of chapters ago, I did a little kind of a demonstration I do with my class, showing you the scale model between the moon and the Earth. And we did a tennis ball, we did a basketball, and then we upgraded and we went up to an exercise ball size. And I tried to emphasize the fact that there's a lot of space in space, right? But it turns out the space is not completely empty. There is quite often a low density gas and even some dust there, what's called the interstellar medium. And it is, even at its densest, not very dense compared to, say, the Earth's atmosphere. But the interstellar medium can get dense enough that it can impact, first of all, how light travels, but also it turns out the interstellar medium can get dense enough to actually form stars. And that's really the whole point of this chapter, is to talk about how stars first come to be. And the first question you should ask yourself is, well, how the heck do we know that there is this gas and dust out there? And it turns out that we know it because starlight can be what's called reddened. And it's the same process, the same reason why we have red sunsets. Why do we get sunsets that are red. And it's because the light from the sun has to travel through a fair amount of the Earth's atmosphere when it's close to the horizon. And as it travels through the atmosphere, the blues tend to get scattered. So here we show an interstellar cloud, but think of this as being the Earth's atmosphere, and think about this as being your eye. The reason why we have red sunsets or red sunrises is because the light is traveling through a lot of atmosphere, and it turns out the blue tends to get scattered more effectively by the gases and dust in the Earth's atmosphere than the reds do, and therefore the remaining light that winds up reaching your eye is slightly reddened. The same argument applies when trying to detect or to prove that there is indeed an interstellar medium. The fact that we have stars that are producing light, and yet they appear to be redder than they should be. And that's because of the interstellar medium in between the star and the observer. Okay, one of the first things to remember in understanding emission nebulae is think back a couple of chapters ago, chapter 6, module 5, when we were talking about the different types of spectra. We had continuous spectra, that was the entire rainbow. We had absorption spectra, which was the entire rainbow minus a few lines. And then we had the emission spectra, which was essentially nothing but a few bright lines. In fact, it's called a bright line spectrum sometimes. That's what's going on here. What happens in an emission nebula is you're looking at a cloud of gas and dust in space. And of course, you shouldn't normally be able to see it, right? Gas and dust, just a cloud of dust, is not normally going to produce its own light. It's not self-luminous, so you should be just seeing darkness, and yet you are seeing a cloud, right? So how is that happening? How is that cloud of gas and dust producing any kind of light? We should be just staring off into the darkness of space, and yet that cloud of gas and dust is close enough to a hot star nearby, and that hot star then excites the electrons in the gas. We talked about the fact that electrons can absorb photons of the right energy, get excited, and then they de-excite. What we're seeing here is that the gas is absorbing light from the nearby star, which is not necessarily along our line of sight. We're looking off, kind of askew to the actual star. So we're not looking at the star, we're looking at the gas off to the side of the star. But that gas is absorbing energy from the nearby star, getting excited, and then de-exciting. When it de-excites, it emits a photon. That photon can go in any direction, off into all directions into space, including the direction that we're observing from. So we're receiving those emitted photons then of this gas cloud, and typically it's hydrogen. And if you recall, in the hydrogen bomber lines, you have a pink, you've got a blue, you've got a kind of a violet. When you combine them all, you tend to get a reddish tinge to that light. So those specific frequencies that are emitted by an excited hydrogen gas cloud are red, a blue, and a violet. And kind of when you combine those, the human eye's sensitivities as well, you wind up with a pinkish light, which is why an emission nebula will kind of look reddish or pinkish. Here's a couple of examples of emission nebulae. But again, these are clouds of gas and dust that are relatively close to very hot stars, stars that are hot enough to excite the atoms in the stars, in the gas, and the gas then gets de-excited, emitting a photon in our direction. In the case of a reflection nebula, these appear blue, and the question is why? Well, it's again a cloud of gas and dust relatively close to a star, but in this case either it's not as close or the star is not quite as hot. So instead of exciting the gas and causing the gas to then de-excite and emit its own photons, in this case the gas and dust is not getting excited and it's not producing its own light, but it's just scattering the light from the nearby star, or it's reflecting it. And as we talked about just a couple of slides ago when we talked about why sunsets are red, well, think about why the sky is blue. The sky is blue because light is coming into the Earth's atmosphere, and unless you're looking straight at the sun, the light comes in, let me use yellow here. Light comes in to the atmosphere from the sun. And obviously if you're looking straight at the sun, you're going to see the sun. It's going to be kind of yellowish white. But if you're looking not at the sun, if you're looking off in say in this direction, well, what are you seeing? Well, you see blue sky, but why is the sky blue? It's because of the atmosphere being there. because the sun's light does not just come in one particular direction. It's actually going in all directions. It's coming in to the Earth's system in this direction, and this direction is looking straight down. Now, obviously, the light that's coming straight down comes straight into your eyes, but light that's kind of, when you look off and not look at the sun, if you're looking just at another part of the sky, if you were on the moon, you would see nothing but the blackness of space because there's no light coming in. But because we have an atmosphere, the light from the sun comes in and gets scattered by the atmosphere, the molecules of the air, mostly nitrogen and oxygen. And the air molecules tend to scatter blue better than they scatter red. And so therefore blue winds up, of that light that's coming in, blue gets scattered in all directions better than the red. And so therefore you see, instead of seeing nothing when you look off in this direction, you see blue light coming into your eyes. That's why the sky appears blue. Same thing with reflection nebulae. What happens is the light from that star, that nearby star, is going off into space in a direction that we wouldn't see. But it gets scattered, preferentially the blue end of the spectrum gets scattered and gets scattered in our direction. So therefore, instead of seeing nothing, we do see something. We see the reflected blue light off of that cloud of gas and dust. And finally, we get to dark nebulae. And dark nebulae, again, is just a cloud. Remember, nebula means cloud. Nebulous thinking, nebula. So it's a cloud, and it's called dark because it's a dark part of the sky. So you may see stars and stars and stars, and then you might see an area where there are no stars. And the question is, well, gosh, why aren't there stars there? You would think, since the rest of the sky is populated by stars, that there should be stars in that region, and yet you're not seeing them. Well, it could be A, because there is nothing there, or B, there's stars there, but we can't see them because there's something that's blocking the light. And that's indeed what's going on here. It's a very dense cloud of gas and dust that is blocking the light from behind, and therefore we call that a dark nebula. So we have this cloud of gas and dust called a nebula. Terrific, wonderful, big deal. Turns out that these nebulae are important because they can be regions where new stars are born. How is that possible? Because quite often there's a nearby shock wave. It could be from an exploding star called a supernova, and it's that shock wave that kind of smushes the cloud just enough. Because remember, as we learned in chapter 8, when we talked about the solar system and how the solar system came to be, that solar nebula theory, you start out with a cloud of gas and dust that just gets contracted just enough that gravity starts to take over, and it starts to essentially crush down on itself, spinning faster and faster. And that's essentially what happens when you have this big cloud of gas and dust and you have a nearby shock wave that passes through. It can just get things close enough. Remember, the closer two objects are, the more gravitational force they have on each other. And so you squeeze your cloud of gas and dust just enough that the gravitational force essentially takes over and the whole thing starts contracting. Now you can get not just, these clouds of gas and dust are so huge that they can produce actually more than one star. They can kind of break up, as this lower image indicates, where you can actually get dozens, hundreds of stars being produced from one cloud of gas and dust. So once you go from a nebula to a contracting nebula, things start to heat up. And once things start to heat up, they start to become more luminous. And so you get to a point where the star goes from being a cloud of gas and dust to an actual protostar and then to a star. And we have what's called the birth line. That's essentially when nuclear fusion actually initiates. So up until then, most of the heat, most of the luminosity is coming from, remember, luminosity is dependent upon the area and the temperature. So as this cloud of gas and dust does warm up, it's going to become more luminous. But most of that warming occurs from gravitational collapse. And it's not till fusion takes over that you wind up creating a real star, because at that point it is producing its own energy via nuclear fusion. As you probably recall, that we talked about the sun already back in chapter 8, as far as how it produces energy. And of course it produces using the proton-proton chain, turning 4 hydrogen protons into a helium nucleus and giving off energy in the process. It turns out that more massive stars than our sun actually do almost the same thing. They take hydrogen protons, turn them into helium through fusion, but the process is a little bit different. It's called the CNO cycle. It uses carbon, nitrogen, and oxygen as kind of steps along the way. to producing that helium. And this is actually a more efficient way of producing energy. And that's why these more massive stars, they can do it, and they do it, and they almost have to because of the extra amount of gravity that is crushing them. They have to produce energy in a more efficient way. In this case, it's the CNO cycle. Okay, so one of the very important topics for this chapter and for the life of a star is hydrostatic equilibrium. That sounds really fancy. It really gets down to pressure. You think about how you feel when you dive to the bottom of a swimming pool. What do you feel? You feel pressure, right? Well, where does that pressure come from? It comes from the weight of the water on top of you. Turns out the water is pretty heavy stuff if you've ever carried a lot of water a long distance. Water, just a cubic foot of water weighs like 60 pounds, 62 pounds in fact. So when you're 12 feet down, that 1 foot square column of water that's on top of your head, you stack, 1 cubic foot on top of another cubic foot, et cetera, 60 pounds plus 60 pounds, you can have like 700 pounds of water on top of you. And that registers in your ears as pressure. Same thing happens when you're in a star, right? It's the weight of the plasma on top, the weight of the gas on top creates pressure. It's that crushing force of what we call gravity that is squeezing inward on the star. The only thing that helps to combat, just like for you would be crushed by water if it wasn't for the fact that the bone structure of your body helps to resist that force. Likewise, the radiation pressure of the energy that is generated at the core of the star produces an outward force that keeps the star at equilibrium for most of its life. That's what's considered hydrostatic equilibrium. And got kind of a similar diagram here with this guy with a bunch of books on his head. The more layers on top, the more the pressure is going to be. So that's why the pressure 12 feet down in a swimming pool feels different than when you're only 1 foot down in a swimming pool, because there's less weight of water on top of you. Same thing, the farther you get into a star, the deeper down, the closer to the core, the greater the pressure is going to be. Okay, so big stars live fast and die young. Sometimes the analogy is given where you think about gamblers at say a blackjack table, and you got this high roller who comes in with a huge stack of chips. Well, that's kind of like a large, very massive star. Very massive star has a lot of fuel to work with, has a lot of hydrogen, but just like the high roller, the guy with the big amount of chips is also going to be betting large amounts on each hand. And that's what happens with large stars. Large stars have so much mass, they have a huge crushing force of gravity, and therefore they must generate a lot of energy to essentially just resist that crushing force of gravity. So therefore there must be a lot of fusion going on that consumes a lot of fuel in a hurry. So this is the big spender, the guy with the big stack, who's putting in a lot of chips per hand. Whereas a more modest star like our sun has a more modest pile of chips, but also is betting more conservatively on each hand. And therefore, the high roller is going to blow through his stack of chips in a shorter time period than the conservative gambler. Same thing goes on with stars. As you've already seen at the end of chapter 13, the life expectancy for a sun-like star is much larger than much longer than life expectancy for a star farther up and to the left on the main sequence.